Hello everyone and welcome to my channel. Today we're going to discuss a fundamental concept in algebra called Descartes' rule of signs. This rule is a handy method to determine the possible number of positive and negative real roots of a polynomial equation. We'll explain this rule, walk through its logic, and give some examples to make it more clear for you. And by the end of this video, you will be more confident in applying this rule to any polynomial you meet, and let's dive in it. So, what is Descartes' rule of signs? Descartes' rule of signs provides a way to estimate the number of possible and negative real roots in a polynomial equation based on the signs of its coefficients. Now, using Descartes' rule of signs, we can find possible number of positive and negative real roots of any equation. So, in order to find positive real roots, first of all, we write the polynomial in the standard form with powers of x in descending order. We count how many times the sign of the coefficient changes from one term to the next. Each sign change represents a possible positive real root. The actual number of positive roots could be equal to any number of sign changes or less than that by an even number, even for instance 2, 4, 6, and so on. Now, how to find the possible number of negative real roots in any polynomial? First, we replace x with minus x in the polynomial. Then we simplify the whole expression, count the sign numbers in the coefficients of new polynomial, and finally, actual number of negative real roots is either that number of changes or less than that by an even number. So I've prepared a step-by-step guide on you how to use this rule, how to apply it. First, all you need to do is write the polynomial, make sure it's in standard form. Second, count all positive real roots. Identify the sign changes in original polynomial. Then find negative roots, substitute x with minus x, simplify and count sign changes. And finally, interpret the results. Total number of positive and negative roots helps you estimate the possible roots of the equation. Now we'll go over some examples to make it clear for you. Let's take a polynomial p of x, which equals to 2x cubed minus 5x squared plus 3x minus 4. So, first of all, let's find its positive roots. We first of all take the coefficients of the whole polynomial. So here we have 2, 5, minus 5, 3, and minus 4. So once we identify the coefficients, we need to identify sign changes. So for example, from 2 to 5, the sign has changed from positive to negative, so this is 1. From minus 5 to 3, the sign has changed from negative to positive, this is 2. And from 3 to minus 4, the sign has changed from positive to negative, which is 3. So we have total sign changes, the number 3, which using Descartes' rule of signs, we can therefore find out that the number of positive real roots of this equation is either 3 or less than that by an even number. For example, minus 2, which equals to 1. So we have possible real roots of this polynomial p of x, 3 or 1. Now, what if we want to find possible number of negative real roots of this equation p of x? What we need to do is substitute minus x instead of x in the whole expression. So we put p of minus x, which equals to 2 times minus x cubed minus 5 minus x squared plus 3 times minus x minus 4. Now we simplify it. So what we got here is new coefficients, minus 2, minus 2, minus 5, minus 3, minus 4. So again, we need to find all the sign changes from minus 2 to minus 5. We have no changes as number was negative and it remained negative. From -5 to -3, we have no changes in signs, negative to negative, and same here, no change at all. So what we get is a total sign changes of 0. And as we remember, um, according to Descartes' rule of science, if there is no real sign change, then there is no possible number of real negatives or positive solutions to the equation. So therefore, number of negative real roots is 0. And now we'll look at the final example to make it more clear. So finally, let's take a look at another polynomial. This is polynomial q of x. It has x4 with x in the power of 4 with coefficient 1, minus 3x cubed with a coefficient -3, plus 2x squared with coefficient +2, and x with coefficient 1, and -5, coefficient -5. So first of all, let's write down all the coefficients. 1, -3, 2, 1, -5. Let's find total sign changes. From 1 to -3, we have one sign change from positive to negative. Here we have sign change from negative to positive, which makes it 2. From 2 to 1, both are positive, so there is no sign change. It remains same, 2. And from 1 to -5, we have a sign change from positive to negative, which makes it a total number of 3. Total sign changes is 3. And as we know, the possible number of positive real roots of this polynomial will be either 3 or a number less than that by an even number. So 3 minus 2 makes it 1. So we either have 3 or 1. Now, let's take a look at negative possible real roots of this equation. What we need to do is substitute x with minus x. So what we need to do is simplify it. And we need to find the coefficients. We have here coefficient 1, coefficient +3, +2, -1, and -5. Let's write them down. 1, 3, 2, -1, and -5. Let's take a look at changes, sign changes. So from 1 to 3, there is no sign change. Both are positive numbers. Same with 3 and 2. Both are positive numbers. No sign change here. From 2 to -1, there is one sign change from positive to negative number, which makes it 1. And from -1 to -5, there is no change, which leaves us with total sign changes of 1. Now, as we have a total sign change, we cannot subtract an even number from that, and we can't get negative number of real roots, so we'll have one total negative real root of this equation. So you need to keep in mind a few things. The rule only tells you possible number of roots. It doesn't guarantee exact count. That's why we have, as you can see, in the previous examples we had um, we had either 3 or 1 by changing it by subtracting an even number from the total sign changes. We do not get the exact number, and you should also keep in mind that remaining roots, if there are any remaining roots, they may be complex. So I hope this explanation and these examples have clarified the concept for you. Thank you for watching, and feel free to ask any questions in the comments.